So welcome back, dear students, to this aerospace testing. Last Tuesday, can you hear me? Can you see the screen first?
Yes, Professor.
Okay, so last Tuesday, we start analyzing different type of estimating methods. Estimating, we are referring, of course, to the system transfer function according to the different excitation type. And we analyze different approaches related to the what we call modal appropriation, sign excitation, harmonic excitation, sign sweep, periodical. Then we move to the random excitation, and we saw together the usefulness of the H1 and H2 estimators. And then we move to this plot that is the estimating process associated to the excitation of the structure done by the impulse, done by a modal hammer, as we call it. And we found out that instead of exciting the structure with theoretical Dirac, that is a theoretical impulse, we excite the structure with a practical Dirac having a duration that we call B. And the Fourier transform of this Dirac with a duration B on the structure is leading us plot that I just drawn here, in which we are having as a function of the of the of the term omega b half, we are having the plot of the different cardinal signs. And as we can see, when we're looking to the, let's say, reference curve, we are having that instead of exciting, and that is the way we have to look to this plot, instead of exciting all the frequency with the same amplitude, with the same level of excitation, we are exciting the structure with a reduced amplitude of excitation as a function of frequency. Worse, we are also having by this plot some parts in the omega b half axis that are not excited at all. And of course, this zero excitation, that is the crossing of your curve with the x-axis, is happening at the nodal points that here in this representation are half pi, pi, pi fourths, and so forth. Um, how can we, and also we also consider that your B, the duration, depends on the hammer configuration. If you go back to your notes, you will you can see that this B depends on the mass and or the stiffness of your hammer. The higher the stiffness, the shorter is the duration time, and therefore the longer will be the wavelength. On the contrary, in this plot, of course, on the contrary, the lower the hammer stiffness, and then what we are having is the shorter is the wavelength. As we can see there, we can now let's see how we can use those plots in order to have a practical use of the hammer. What we have to do is, let's say, start with hammer configuration in terms of mass, in terms of stiffness, and then what we have to do is just see and then prescribe how much is the acceptable attenuation of your signal. What does it mean? That it means that you have to decide what is the reduction of the amplitude of vibration that you can accept in your analysis. That is, you have to check that your reduction here is the one that you are expecting, it is the one that you are accepting. Okay, so that is attenuation. Okay, and this is attenuation, for example, could be negative 3 dBs, for example, or negative 10 dBs. It depends a lot on the on the on the test itself and on the accuracy and on the capabilities that you are having in your experimental setup. So it depends a lot. But once you choose that, you have the reduction. That reduction, once again, is telling you what is the attenuation that you are accepting by, and therefore giving you information that this attenuation is the maximum that you can see, that you can have, before telling that the signal is too low, the signal level is too low, the signal to noise ratio is too low. So once you decide that, you enter to this plot. Now let's figure out that you are having one of these three curves that I just shown, that is coming from your testing, okay? And then by using that, you can go, okay, on a horizontal axis like that. And then let's cross the one of the line, for example, the first one, the second one, and the third one like that. So this crossing with this information of the x-axis is telling you the maximum frequencies that you can excite within your configuration, within your acquisition setup, that is exciting the structure with the prescribed amplitude of vibration. So what you're having is this one, or the blue one, or the red one. Okay, so these are the frequency range, okay, F max, so maximum frequency, for the green Hammer configuration, and maybe it is characterized by having low Hammer stiffness or a large mass, or we are having F max, that is the maximum frequencies with the reference, let's say, Hammer configuration, or the last one is the maximum frequency when you are considering, for example, Hammer configuration characterized by a very high Hammer speed or a very low Hammer mass. Okay, so as you can see, what we can say is that your frequency max, red, is of course larger than your frequency max of the reference signal in blue, and that is in turn larger than the maximum frequency of your model Hammer configuration characterized by a low stiffness or high mass. Okay, so what we are having is here, if that is your reference frequency, okay, then you can say that this one is red frequency max is characterized by higher stiffness or lower mass compared to the reference one, or the green, okay, is characterized by having lower stiffness or higher mass. Okay, so once again, I'm writing these steps. First, steps, let me have steps to choose the hammer configuration. So the first step is set the reference values of K and M. That is the stiffness and the mass hammer parameters. How can you do that? You can have softer or stiffer hammer tips. There is a selection in your hammer setup, or you can also add or remove some masses from your hammer. That is practically there are some practically tools that allow you to do that. Then set the allowable attenuation of the input excitation. Okay, for example, we saw that negative 3 dBs or negative 10 dBs. Okay, or you have to choose that according to your accuracy, desired accuracy, to your hardware, available hardware that you got. Okay, then second step, okay, look from the PSD of the hammer. Remember, we are in the frequency domain. The frequency that corresponds to the allowable attenuation, and that is telling you what is the maximum frequency that you can excite with the prescribed attenuation level. Okay, so once again, from this plot, okay, you have, for example, your reference value, the blue one. Select your attenuation, negative 3 dB, and then you can see that the blue frequency maximum is the one that you are considering. Now the question is that okay? Then you are very happy. If not, if you need higher frequency range or lower frequency range, then you have to change the setup accordingly. Okay, so the last step, fourth, if the identify F max is okay, then stop, you are ready. Otherwise, change the hammer tip configuration. Okay, that is, you can, for example, increase or reduce the maximum frequency because you are interested in a specified frequency range. Okay, one possible discussion is, for example, my job is to identify all the natural frequencies, all the molar parameters in a given frequency range. Okay, so if I am using the mono hammer, I have to do this preliminary test and check that this maximum frequency to which correspond the acceptable attenuation level is higher or at least equal to the prescribed maximum frequency of interest. Okay, if not, then you have to change. On the other side, what we can say is that if you are willing to excite just the very lower frequency modes, then you can think to excite the structure with a number tip that is very soft and with a number having a very large mass, so that all the energy that we are going to introduce is acting at the very first frequencies, okay, very first low frequencies. That is, we are in a green behavior, just to say, just referring to this picture. Okay. On the contrary, if you want to excite the structure with a very large broadband frequency of excitation, then maybe you need to go with the red curve. That is, you have to characterize, you have to configure your hammer with a very stiff tip and with a very small value of the mass. Okay, I hope that is uh, clear with you. Okay, if not, please, I'm here and ask me all your questions. Okay, if there are no questions, let me introduce now a different way to excite the system with respect to the hammer. The other way is the shaker. Okay, so the shaker is something transducer that is capable to transduce whatever electric wave, okay, into a corresponding mechanical wave. How can you do that? By considering a coil surrounding a movable rod that is operating in a magnetic field. Okay, so with the magnetic interaction, we can feed your coil with your whatever, with your desired mechanical wave in a in the shape of an electrical wave. This electrical wave is interacting with your electromagnetic magnetic field, and therefore the reaction to that is a motion of a movable rod. And this rod, of course, is connected to the structure in a way so that we can transfer the energy with the shape that we are giving with your signal analyzer to the structure, and therefore we can extract the structure. Okay, so the shaker first is a coil surrounded by a movable rod. Okay, that is operating in a magnetic field. Okay, so for example, we are in this condition. This is your movable rod that is a solid electromagnetic material, just like, for example, steel. Okay, then we are having your coil. Okay, so this is your rod, then coil, like this, and this coil, okay, is controlled, for example, by an AC current, okay, that is representative of your shape. Then this coil is, sorry, this rod is connected to somehow your, this is your mass, okay, to your reference system. Okay, and then what we are having is sort of magnetic field like that. Let's say north, south. Okay, so this is the magnetic field. Okay, this is the input that is representative of the input excitation. These are a fixture to the ground. Okay, and as a result, what you're having is, in this case, horizontal motion, okay, of your rod. Output motion with the shape of the input excitation. Okay, so what is happening is that injection an AC into the coil then what's happening? The rod will move axially. Thanks to the electromagnetic interaction, okay? But the important thing is that this motion is following the shape, okay, of the AC current that we are feeding, they're using to feed the system, okay? Thus, transferring to the system a dynamic loading. Okay, and that's the reason why we are going to use such a system to excite the structure. So just to link this to what we already discussed, for example, when we are going to excite the structure with a harmonic, with a sinusoidal excitation, the very first approach that we saw together that we can use to estimate the transfer function, the system transfer function. So we are going to excite the station, start the system, that is, we are going to have an input excitation that is just a sinusoidal wave of the given frequency and a prescribed output. The resulting electromagnetic field is transducing the current, the input current, into an output motion. Okay, that is just having the same frequency, and we have just to tune the value of the parameters, the gains, in order to have the desired output as well. Okay, what we can do with this kind of excitation is that there is such a transfer transfer of the energy from your input side to your structure that is considered your output side. Okay, and of course we need to have the required electrical power to correctly excite the structure, and we have to consider the right parameters of this electromagnetic field, that is number of coils and the values of the permanent magnets, so that we are exciting the structure with the right response and the frequency range of interest. Okay, so in the structural dynamics, for example, these are mainly considering the frequency range of about some hertz up to about some kilohertz. Okay, using the shaker, it is possible. So using the shaker, it is possible to choose the shape of the input signal from the following ones: random, sine sweep, pseudo-random, shock, and other specific input shapes, according to the different type of the test that we are going to run. So as you can see, there is a huge difference between the shaker excitation and the hammer excitation. With the hammer excitation, what we are doing is just excite the structure with a, let's say, impulse-like excitation shape, okay? And we discussed that. I'm not going to discuss that right now. On the contrary, when using the shaker, you can have a variety of excitation types from random to shock and whatever, okay? So you can have a better control of your input excitation in your analysis. However, we are not having just pros of this excitation system because we are also have some errors, some cons of this type of excitation system. The most important one is what we call the insertion error, okay? And that's the reason why we are going to consider that insertion error. And that is always to take into account. And what is the source of this insertion error? Due to the relevant mass of the shaker and that is because, remember, we are going to use of the permanent magnets, okay, in order to create an electromagnetic field that is interacting between your input electrical current. Okay, so that's the reason why generally the shakers are characterized by very large mass compared, for example, to a monohammer. Okay, but they are very weighty. Okay, and also we are having the mass of the shaker also very large because we would like not to interact with the system itself. We would like to let the system vibrate only and not vibrate with the shaker. So we need to have the mass of the shaker high also for decoupling reasons. Okay, so the real mass of the shaker, and I can write that, remember, the permanent magnets and decoupling reasons. Okay, because of that, because of this relevant mass of the shaker, the dynamic mass is affected by such an error induced by this large mass. Okay, such an error is limited by using what we call a stinger. Okay, let me write that and then I'm going to explain this. This error is limited by using what we call
a stinger. What is a stinger? Let me show the typical configuration. So we are having, for example, your supporting structure like this. So that is your support. Then we are having the basement, which is connected to your shaker, something like that. Okay, and then finally we have your shaker, for example, in a horizontal position. Okay, and then here we have your stinger that is a rod with a very large axial stiffness, with a very low um, bending stiffness, so that the shaker can transmit the vibration only in one direction. Okay, it is of course our shaker. We are having the stinger here. And then just before connecting to the structure, we are placing a load device, for example, this, that is your load cell. That is capable to transduce, as we saw, the motion into the equivalent dynamic load that is transferring to from the shaker to the stinger until up to the structure. And for example, that is your whatever structure that we would like to measure this dynamics. Okay. Generally, this stinger is made of steel or nylon. What do they have? Must have is a very high axial stiffness and low bending stiffness. Okay. With this device, what we are seeing is that we can also control the excitation direction through this stinger. Okay. And why that? Because the effect of the stinger, sorry, is just to consider the excitation direction that is just acting in the highest axial stiffness direction with respect to the lower one, because they are not having any introduction, any control to that. Okay, so that is typical of your shaker system. Just to make a comparison with this shaker system, let me consider also the hammer. Okay, here together with the shaker, just to complete the vision. So let me consider the model hammer. We are not going to review the properties and to discuss the capability, but just now comparing the use of this model hammer to excite the structure with the shaker excitation, we can say that by using the model hammer, we don't have any insertion error due to the very low added mass. Okay, so we can write that no insertion error due to practically zero added mass, okay, compared to the shaker, of course. It is very useful because by using the mono hammer, we can have a very fast testing. Okay, we do not have to make all the connections, all the cablings required to set up the shaker. Okay, measuring chain. Okay, then we can also say that by using the mono hammer, we are having a broadband excitation with a short excitation time. Okay, and that is one of the most advantages of that. Let me write this. Broadband excitation with short excitation time. And that is one of the most convenient properties of that. Please note that I'm just writing that once again. Okay, if hammer mass is increasing, then what I call the maximum frequency for a prescribed attenuation level is decreasing. Okay, but however, what we can say is that within the frequency range of interest, okay, the excitation level will increase. Okay, of course, the frequency range is shorter than the other configurations. On the contrary, if the hammer stiffness is high, then your maximum frequency for a prescribed attenuation level is increasing, but the excitation level is decreasing, because once again the energy that your first could transfer to the system is practically the same. So if that energy is spread over a larger frequency range, then of course we can't we have to just a lower excitation level. Okay, so let me show you, before closing the class, let me show you some very brief overview of some other excitation types. Okay, one of them is referring to the laser Doppler vibrometer. As you can see, this laser Doppler vibrometer is a non-contact. Sorry, once again, you have to rotate, but I'll give you the copies of these information straight from the BNKey to you. So the non-contact vibration transducer are very useful when we are, for example, dealing with structures that are very difficult to be in contact, like hot parts or some operating structure that is very difficult to do that. Okay, these are typical shakers. Okay, from the smaller one to the bigger one. Okay, they can have a lot of tools that help you in taking the test. Okay, for example, supporting structure, set of stingers, and supporting once again. Okay. On the contrary, that is, in addition to that, here are some representative of the modal hammer. As you can see, we have different modal hammer sizes according to the different frequency range of excitation. Remember, larger hammers means that you are exciting lower frequency range, smaller hammers, higher frequency range. And then we have also the chance to change the tips, the masses, as you can see from this picture, according to what we already discussed. Okay. How many channels? If you would like to become a model tester, an engineer that is experienced with the model tester, then you have to consider that the number of channels made a difference. So if you have a low number of channels, then you can just have a troubleshooting analysis. If you have a mid-size system that is with the number of channels equal to, let's say, 10 to 30, then you can do a very interesting analysis. If you would like to be very specific and then for have a very refined analysis, then you need about 30, even more channels. Okay. Here is the general setup. I don't want to take time with this, but with that, so this is the general setup with the model hammer. Okay, you have a number one input. Okay, then we have different outputs using the accelerometers. Then there is the acquisition system. Okay, and this acquisition system is driven, is controlled by a computer program that could be a computer laptop, desktop, whatever, according to your specs. Okay, and of course, in order to do that, you need some model analysis test softwares and control everything that we are doing during these tests. When we are considering a shaker excitation, then you need to add, compared to the previous one, an additional item that is the power amplifier and the shaker itself. The general layout is the same, but you need to control the power amplifier that is driving your shaker. So you need to have also an additional channel that is measuring that is giving the right signal to the shaker. Okay, and then once we are at the shaker stage, we need just a force transducer that is collected. Those data are collected by the acquisition system, as we have already have with the hammer. Okay, if you go a little bit higher, number of channels, this is the vision. Okay, even larger. Okay, and then if you are going to do a full multiple input, multiple output analysis, then maybe you can have more than one acquisition system that are connected all together in order to save the the synchronicity of the signals, and therefore you have to control your test with a little more careful in doing that. Okay. That's it for today. Thank you for your attention. Questions?
Professor,
Yep.
Professor, I have a question about laboratory. I saw one of the video and thank you, it had a good quality. So I want to know, writing the reports for experimental matter is mandatory?
Okay. So let's have a few words about the laboratory activity. I upload the two laboratory activities, laboratory number 1 and 2, the corresponding materials, okay, in terms of Excel spreadsheet, so that we take the measurements for you, okay, and I also upload the text of these laboratory activities, number 1 and 2. So what you have to do is read carefully the text first, starting from laboratory number 1, go through all the items and all the questions, and then watch my video that should be the actual reality if you were in the laboratory. Okay, so watch the video, understand what I'm doing, and then use the data that I gave you in order to answer all the questions. And then once you are done with that, following what we already discussed on how to write a report, in that, write your report, okay, with the statement, basic statements, theoretical derivations, some results, concluding some marks. Okay,
There is not a deadline to submit these reports, so you can do that by yourself. But if you want to start your final exam with those reports, you should upload, you should give them reports to me well before the start of the exams. And so let's say 1-2 weeks before the final exam, regardless the date, of course.
Okay, so and if we prepare the experimental report, how is the final exam?
How the final, sorry?
I mean, how is the final exam if we provide the report before
Oh,
the
it depends on the final exam that you choose. I think that you go to the InfoStud system, you can see the dates for the final exam. So if you choose the first date, then consider 1 week before. But also if you choose whatever date, the final reports should be available to me at least 1 week before.
Okay, and can we do this in a group?
no, there is no grouping.
Each report is personal. You have to write your own report. Okay?
Okay, thank you.
You're welcome. Other questions?
And also, how many laboratory activity do we have?
I'm planning 4 laboratory activities. 5, sorry, 4 or 5, depending on the time.
Okay, thank you.
Maybe 5.
Okay.